Okay, so this is generalized linear models with examples in R. We're in chapter 4, question 4.3. So we have two parts here. We're told that the book made two statements concerning the log likelihood, and we're now going to prove those two statements. Okay. So in all of this, we're assuming that y is a continuous variable. Okay. So the first one is, working with just one observation, use the definition of expected value to show that the expected value of the score function of our parameters or parameter zeta is equal to this term here, right? Which is the derivative, or maybe partial derivative, if we have more than one parameter here, of the likelihood, basically. Okay, so so let's just kind of break this apart here. So let's just look at the definition of expected value for a continuous variable. So it's this, right? So it's the value times the probability of that value, and sometimes that probability is conditional, and so we have that. Okay. If the probability of A is not conditional, then we have this. Okay. All right. So next we have the score function. And so remember that the score function is the derivative with respect to a parameter of the log likelihood. Okay. It's not the likelihood, but the log of the likelihood. Okay. And if we have more than one parameter, right, if zeta represents more than one parameter, then we're using partial derivatives instead. So okay. So if we kind of apply those two things to the expected value of the score function, okay, so I'll take my definition of expected value. Okay, so I have this. So I'm trying to find the expected value of the score function. So I take the value of the score function times the different possible values of zeta, right? Because zeta is determining the score function, right? Or the value of the score function. So I just expand now the score function. Okay. So I've expanded all the way to the log likelihood right here. Okay. And then it turns out that that all of this is 1 over, oh, I'm missing a parentheses there. That's okay. So it's 1 over the probability of zeta times this. Okay. And so now I'm just regrouping terms here. So I have this, and I put them inside of the parentheses, which may be a little bit misleading, but and then I'm just taking this outside. Okay. Well, now this cancels with this, and so I have 1. So now I'm just left with this term here. Okay. Well, this is what we're meant to show, right? So the next thing we're supposed to do is to show that this expression, right, equals 0. Okay. So I take my expected value of the score function again, which we've just shown to be what we're supposed to show it to be. Okay. And I'm just going to rewrite this just for a little bit clearer notation. Right. So I have the derivative of that. And then it turns out that I can take the derivative and the integral in either order. So I'm going to take the derivative outside of the integral. Well, now, this right here, as I'm looking at this, I'm realizing that I'm accidentally transposing the zeta and the y here. I think that's maybe a little bit confusing. So apologies for that. But I'm just going to kind of keep moving. So I can take these in either order. Okay, and so I take the derivative outside the integral, and now I have the probability distribution, and from negative infinity to infinity, and by definition, a probability distribution has its integral is 1. So I have the derivative of 1, and that equals 0. Okay, so now we've shown that the expected value of the score function is 0, which is what we were meant to show. Okay, now in part 2, we are using that the expected value, we're taking what we just found, that the expected value of the score function being 0, and then we're supposed to show that the variance of the score function is this, which equals the Fisher information. Okay, so I'm going to do this in 2 parts. So first I'm going to show that the variance of the score function is this guy, and then I'm going to expand this guy to a term or to an expression which is equal to this. Okay. All right. So first let's start with the variance. Okay. So I can always write variance like this. Okay. All right. So it's just the expectation of the squared difference of the value minus its expected value. Okay. And so if I take this term right here and I multiply it out because I'm squaring it, I get this right here. Okay. And then I can do I learned it as FOIL, right? So I multiply u by u, and I get the score function squared, and then I multiply this by this, and then this by this, right? So I'm multiplying u by its expected value twice. Okay, so I get negative 2u times the expected value of u, and then I multiply the expected value, the negative expected value of the score function times the negative expected score value of the function, so I get the expected value of the score function squared. Okay. Well, we just showed that the expectation of the score function is 0, so that term drops to 0, and then we see that again right here. Okay, so that term becomes 0, that term becomes 0, which means all of this becomes 0, which means that we're just left with that right there. Okay. Well, now if we have just one parameter zeta, well then this would be a perfectly acceptable way to write it. But if zeta represented more than one parameter, right, in other words, zeta is a vector, well then in vector notation or matrix notation we would write it like this. Okay, so there we go. So now I'm going to expand. I'm just going to keep working with this right here, probably because more people are familiar with doing calculus on scalars rather than matrices. And we can always translate between the two if we need to. Okay, so the expected value of anything, we already found that. So I need the expected value of the score function squared times the likelihood here. I am just continuing to screw these up. so apologies for that. But anyway, but we'll just kind of keep pushing here. So if I have this. Okay, that is the derivative with respect to the log likelihood right there. Okay, and now if I take that derivative, well now it's 1 over the inner function times the derivative of the inner function, or 1 over the outer function times the inner function. So I got that. Okay. So now I'm just going to stack this on top of that and distribute the square. And one of these squares cancels, and I have, right, so one of these values cancels with this over here, and I'm left with this expression, and that isn't really illuminating. It turns out that this is the Fisher information. But just to show that, I'm going to take the Fisher information as the second derivative of the log likelihood. Okay? And then without going through all of the steps of the calculus, hopefully you can follow it, and hopefully I've done it correctly here. But we go through, and we arrive at the same expression, right? So here I found that the Fisher information equaled this, and I also found that the variance equaled, the expected value of the score function squared, or or the matrix equivalent, and all of that equaled that. Okay, so kind of the line of reasoning was that the variance equaled this, equaled this, equaled the Fisher information matrix. So yeah. So anyway, we'll call that good.